Hello everybody and welcome to our second video lecture. Today what we're going to talk about is cylindrical coordinates. This is one of two new coordinate systems that we'll introduce in order to make integrating in 3 dimensions much easier in certain situations. The other coordinate system that we'll talk about next time is spherical coordinates. Both coordinate systems can dramatically simplify problems in certain situations. The coordinate system that we're used to is Cartesian coordinates. In the Cartesian coordinate system, a point is described by a triple of values x, y, z. So for example, if I was to describe the point 1, 3, 2, then what I would do is I'd draw some x, y, and z axes. On my x-axis, I go over 1 space. On my y-axis, I'm going to move over 3 spaces. Now if I draw a line parallel to the y-axis passing through that point 1 on the x-axis, like so, and I draw a line parallel to the x-axis passing through 3 on the y-axis, like so, I'm going to be interested in this point where those two lines cross. If I move up from there 2, then I'll be at 1, 2 on the z-axis. So what I'm going to do is I'm going to start at that crossing point and I'm going to move up exactly that same amount parallel to the z-axis. So about here, say. So about there, and the point that I get is that exactly that point 1, 3, 2. So that's how Cartesian coordinates work, and that's something that we're all very familiar with probably already. Cylindrical coordinates work a little bit differently. In cylindrical coordinates, a point is again described by a triple of values, but this time instead of x, y, and z, it's r, theta, and z. So if I want to describe a point in 3-dimensional space, let me again draw our x, y, and z axes, and if I want to describe a point here, say the point 2 pi over 6, 1. The first entry is r, which is 2. So I'm thinking about a point in the xy plane which is r away from the origin. So the radius, r here is a radius inside the xy plane. Theta here is the angle pi over 6. So what this corresponds to is a point in the xy plane formed by a vector of length 2, where the angle between the x-axis and that vector is given by pi over 6, which is about 30 degrees. And by about 30 degrees, of course, I mean exactly 30 degrees. The last component there is that 1, which is the z value. So for that, what I'm going to do is I'm going to move up from that point of that arrow. I'm going to move up exactly 1 unit parallel to the z-axis. Make that better here. And if I go up exactly 1, that's the corresponding point. So this point here that I've drawn in our picture is the point 2 pi over 6, 1 in cylindrical coordinates. In terms of Cartesian coordinates, we can express this as well. And the way to do that is to figure out what our x value is, what our y value is, and what our z value is. Our x value here is exactly this value coming right here. And if I'm thinking about this angle and this width here, this hypotenuse of this triangle that I can draw, this right triangle I can draw, the hypotenuse of this is 2. So this value here is going to be 2 times cosine of this angle. So my x value is 2 times cosine of that angle. The y value is similarly given by 2 times sine of the angle. And the z value is just the same z value as before. So in Cartesian coordinates, this is exactly the point 2 times cosine of pi over 6. Remembering that cosine of pi over 6 is the square root of 3 over 2, this is just the square root of 3. And then I have 2 times sine of pi over 6. Now sine of pi over 6 is 1/2, so this is just going to be 1. And my z value is going to be 1 as well. This also shows us that we can convert between cylindrical coordinates and Cartesian coordinates. To convert from cylindrical coordinates to Cartesian coordinates, I'm going to take a point in cylindrical coordinates, which is given by an r, a theta, and a z value, and I'm going to send it to the point where the x value is going to be given by r times cosine of theta. The y value is given by r times sine of theta. And the z value is given by just z. So this is how I go from a point in Cartesian coordinates here to a point in cylindrical coordinates here to a point in Cartesian coordinates over here. To go backwards, I'm going to start with a point in Cartesian coordinates, say some values x, y, and z, and I want to figure out what r, theta, and z should be. My r value here is going to be given by the square root of x squared plus y squared. This is very much like polar coordinates. My theta value, just like polar coordinates as well, is given by the inverse tangent of y over x. And my z value is once again just given by z. Z is z all the way throughout this, and that makes it pretty easy. So now is a good chance to try this at home. Let's consider the following example. Here I want to convert the point 3 pi over 2, 4 into a point in Cartesian coordinates. And go ahead and pause the video right now and give this a shot. See if you can try to convert this point into the corresponding point in Cartesian coordinates. And I'm assuming now that you've tried that at home, so let's go ahead and do this together. To get my x value, all I'm going to do is I'm going to let x be equal to r times cosine of theta. R here is 3, so this is going to be 3 times cosine of pi over 2. My y value is given by r times sine of theta, so it's going to be 3 times sine of pi over 2. And my z value is just given by the same z values before, so z is going to be equal to 4. Now, as we all know, cosine of pi over 2 is 0, so this is going to be x equals 0. Sine of pi over 2 is 1, so y is 3, and z is 4. So in Cartesian, the corresponding point is 0, 3, 4. And let's try to understand this graphically as well. So if I draw myself some axes, like so, then I'm at an angle here of pi over 2, which is 90 degrees. So I'm going 90 degrees from the x-axis, which is this full right angle. So I'm going all the way over here to the y-axis. And on that angle, I'm going up 3 from the origin, because r is 3. So all the way up here, which is 1, 2, 3 away from the origin. And then from that point, I'm going to move up 4 in z. So I'm going to move up 1, 2, 3, 4, which is giving me this point right here. And as we can see, this is going to have no component in the x direction. It's going to, in fact, lie in the yz plane. So that's why x is 0 there. And that's at the point y equals 3, z equals 4, and x equals 0. So this makes sense from a graphical point of view as well. So that's the end of that example. Now, one of the nice things that cylindrical coordinates allows us to do is to easily describe certain surfaces that would have much more complicated equations in Cartesian coordinates. For example, let's figure out what surface is described by the equation r equals 1. If I think about this equation r equals 1, it's a pretty simple equation. It doesn't become much more simple than that. But if I want to rewrite this in terms of Cartesian coordinates, it's going to become much more complicated. So which surface is this? If I remember that r is equal to the square root of x squared plus y squared, then the surface that I have is the collection of all values x, y, and z, so that the square root of x squared plus y squared equals 1. Now if I think about that for a second, all I'm really trying to do then is plot the surface, if I just square both sides, the surface where x squared plus y squared itself is equal to 1. And we know what kind of surface this is. This is a cylinder. So I can graph this in 3 dimensions as well. And at any particular z value, I'm just looking at all the values in x and y so that x squared plus y squared equals 1. And that's going to generate a circle, So this is going to look like a cylinder of radius 1 centered along the z-axis. Fix that picture up with some movie magic there, and this is the surface described by x squared plus y squared equals 1. And here this is my x-axis, this is my y-axis, and this is my z-axis. So this surface, which has this much more complicated expression in Cartesian coordinates given by this expression here, has a very simple expression in terms of cylindrical coordinates. In fact, this kind of justifies the name. In cylindrical coordinates, the constant radius surface is a cylinder. Let's look at a slightly more complicated example. Here I want to think about the surface defined by z equals r. To describe this surface, let's again convert everything back into Cartesian coordinates. So again, I'm remembering that r is equal to the square root of x squared plus y squared, so this equation is going to be z equals the square root of x squared plus y squared. And if I square both sides, this is going to give me z squared equals x squared plus y squared. And I bet we recognize that surface too. This surface is a cone. So if I draw myself some x, y, and z axes here, this is a cone which is centered around the z-axis. Like so. And it also goes the other direction. This is the surface described by z squared equals x squared plus y squared. But I want to notice again that this equation that's defining the surface in Cartesian coordinates is much more complicated than the corresponding equation in cylindrical coordinates, which is given by this equation here. So cylindrical coordinates is simplifying the description of this surface for us. This is going to make our job easier with triple integrals too, because we can describe solid regions in a much simpler format. For example, let's try to describe the set of points above the cone z squared equals 4x squared plus 4y squared and below the plane z equals 4. Now in Cartesian coordinates, this has this complicated expression, but I can reconvert this into polar. Cylindrical, not polar. In terms of cylindrical coordinates, z is remaining the same, but I can rewrite that right-hand side. That's going to be 4 times the quantity x squared plus y squared. And in terms of cylindrical coordinates, x squared plus y squared is r squared, so z squared is equal to 4r squared. Or if I square root both sides, I just get z equals 2r. So that cone again is described by a very simple equation, z equals 2r. So let's go ahead and try to draw a picture of this. I have my x, y, and z axes, and I've got that cone described by z equals 2r, which is this cone which is centered on the z-axis, and is just like the cone picture before except a little bit wider. So there's that cone z equals 2r. The other surface I have in mind is that plane z equals 4. So this is a flat plane parallel to the xy plane. Let's go ahead and draw that in blue here. So here we have the plane z equals 4, and of course it's cutting through the z-axis at that point 4 there. So my goal is to describe this solid orange region, which is that region above that cone but below this plane. And let me call that region something. I'll go ahead and call it E. So as a set, E is given by all the values r, theta, and z in cylindrical coordinates so that theta ranges full circle from 0 to 2 pi, and r ranges from 0 to the maximum possible r value. And how can we figure that out? Well, the way to figure that out is to think about, again, you're going to put a light up here above on the z-axis, and think about the shadow that this thing casts down then in the xy plane. And let's do that shadow in a nice gray shadowy color. I bet you guys can guess here that's going to create some sort of circular shape. This is my shadow. And our idea here is to figure out what is the radius of that circular shadow. And that radius is going to be the maximum possible r value. Well, that radius is achieved when z takes its extreme value, z equals 4, And when z equals 4, I'm going to have 4 equals 2r. So when z equals 4, 4 is equal to 2r because I'm on that surface, that cone. So 4 equals 2r, so then that means that r is equal to 2. So this is the maximum radius. R is at max 2, so r is ranging between 0 and 2. And then finally, what's our maximum z value? So z is going to go between 0, which is that, or excuse me, z is ranging from our red cone down here, and it's going, z is going from the red surface to the blue surface. So z goes from 2r all the way up to z equals 4. And this describes the region that we're interested in as a set. And as we practice some more problems, we'll get better and better at describing these sort of sets in terms of cylindrical coordinates. But that'll be important in order to set up integrals in cylindrical coordinates. Speaking of which, let's try to figure out how to integrate in terms of cylindrical coordinates. So here's a picture of a typical volume element in cylindrical coordinates. Here I'm looking at the Cartesian product of this interval theta to theta plus d theta, r to r plus dr, and z to z plus dz. So this is a box in in cylindrical coordinates. The thickness of the box is dr in this direction, and it's got a height of dz in this direction. And the width of the box is not given by d theta. If you remember how arc lengths work, the width of this part here is actually going to be given by r d theta. So the actual volume element has a volume here, dv, which is given by r d theta dr dz. And this tells us how to convert from a triple integral to an iterated integral inside the cylindrical coordinate system. Specifically, we have the following theorem. If E is the set of all values r, theta, and z, so that theta ranges between alpha and beta, r ranges between g1 of theta and g2 of theta, and z ranges between h1 of r theta and h2 of r theta, then the triple integral of some function of x, y, and z over this domain E is given by this iterated integral from alpha to beta, from g1 to g2, and from h1 to h2 of f of r cosine theta, r sine theta, z. This is saying in particular that I'm converting my x values and y values into r cosine and r sine, just like we would do if I'm converting from Cartesian coordinates to cylindrical coordinates. Let's consider the following example. Here I want to calculate the triple integral of z over the domain E described by the region above the cone, z squared equals 4x squared plus 4y squared, and below the plane, z equals 2. This is very similar to the region that we did in the previous example. The difference being, instead of doing z equals 4 here, we're doing z equals 2. In particular, though, you can describe the region E as the collection of all triples r theta z, so that theta ranges between 0 and 2 pi, r ranges between 0 and 1, and z ranges between 2r and 2. And what I'd like you guys to do is try to verify this at home. And if you're not quite sure how to do that, it might be a good time to go back in the video to where we did the previous example. It looked a lot like this, but describing a region above a cone and below a plane in terms of a set in this form. Anyway, according to the theorem that we just wrote down, this means I can describe the triple integral over E of z dv as an iterated integral from 0 to 2 pi, from 0 to 1, and from 2r to 2 of z, and then the differentials will be dz, r dr, and d theta. And we know how to do it exactly from here. I'm just going to first do that innermost integral. So I'm going to get the integral from 0 to 2 pi, integral from 0 to 1, And when I integrate z with respect to z, I'm going to have a 1/2 z squared, evaluated from 2r to 2, r dr d theta. And this gives me the integral from 0 to 2 pi, the integral from 0 to 1 of, when I plug in 2, I'm going to have 4 divided by 2, which will be 2. When I plug in 2r, I'm going to have 4r squared divided by 2, which will be 2r squared. So altogether, it's going to be 2 minus 2r squared on the inside, times r dr d theta. Now to integrate that next integral, I'm going to have to multiply that out. So I've got the integral from 0 to 2 pi, 0 to 1 of 2r minus 2r cubed. Oops. Dr d theta. And now I know exactly what to do. This will be the integral from 0 to 2 pi of r squared minus 1/2 r to the 4th, evaluated from 0 to 1 d theta. And this is just the integral from 0 to 2 pi of 1/2 d theta, which is just going to be pi. So that's not a bad example starting out. But before I let you guys go, let's try to finish with one more example. So for this example, I want to think about the triple integral over e of the expression x minus y dv, where here e is the solid region between the cylinders x squared plus y squared equals 1, x squared plus y squared equals 4, and above the plane, xy plane, and below the plane z equals y plus 4. So let's try to draw a picture of this setup. So I've got some x, y, and z axes here. And the first cylinder is a cylinder of radius 1, which I'll draw in red here. The second cylinder is a cylinder of radius 2, which maybe we'll do in a nice light blue color. So the object so far looks a lot like a roll of toilet paper you probably have a couple dozen of in your bathroom for who knows what reason. The third surface there is that plane z equals y plus 4. This plane will be parallel to the x-axis, like so, and it'll be that nice orange surface there, which is going to cut through both of those other cylinders. This leaves us with this magenta looking solid region here. Now I want to describe this as a set E, and in order to do that, I'm again going to put that light up at the top of the z-axis. I'm just going to let that light shine down, and I want to think about the shadow that's being cast in the xy plane and the shape that that makes. And the shape that that makes in the xy plane is exactly some sort of annulus shape, consisting of the region between a circle of radius 1 and a circle of radius 2. So to describe this thing in terms of a set, we're looking at the set of points E, which is the set of all points r, theta, and z, such that, well, if I'm looking over here at my xy plane patch, my angle theta is going from 0 all the way to 2 pi. It's going full circle here. So theta will go between 0 and 2 pi. And you can see here as well, r is going between a radius of 1 and a radius of 2. So r is between 1 and 2. And finally, what's z going between? Well, if I look over here at my three-dimensional picture, z is going between the xy plane and this orange plane up here. The xy plane and this orange plane up here. So z is going between the xy plane, which is given by z equals 0, and that other plane, which is given by z equals y plus 4. So between 0 and y plus 4. Now once we have this description of the solid region in terms of this nice set, it's very easy to set up the corresponding integral. So the integral that we wanted to perform was the triple integral over E of x minus y dv. And now by the theorem that I stated earlier, I could rewrite this as an iterated integral from 0 to 2 pi, and from 1 to 2, and from 0 to y plus 4 of x minus y dz r dr d theta. And now we immediately have one little problem in the sense that my variables are z, r, and theta. So I don't want these x and y values. These x and y values here need to be converted into r and theta values. So let me rewrite this integral then as the integral from 0 to 2 pi, integral from 0 to 2, from 1 to 2, and integral from 0 to y is r sine theta plus 4. And I'm doing r cosine theta minus r sine theta dz r dr d theta. Now to actually do this integral, it's worth our time to try to simplify the integrand inside. That is, to simplify this expression here. And one obvious way to simplify that right away is just to write this out. The integral from 0 to 2 pi, integral from 1 to 2, and the integral from 0 to, let's write it this way, 4 plus r sine theta, I think that looks better, of r times cosine theta minus sine theta, dz r dr d theta. And I can even bring that r all the way inside and just make this an r squared, dz dr d theta. Now if I go ahead and do that first integral, there's no z terms involved, so the first integral is very easy to do. And this is just going to give me the integral from 0 to 2 pi, integral from 1 to 2, of the quantity r squared times cosine theta minus sine theta times the quantity 4 plus r sine theta dr d theta. Now to perform the rest of that integral with respect to r, I'm going to have to multiply things out a little bit. And in fact, I can bring out the cosine theta minus sine theta term because it's independent of r, and I can rewrite the whole integral I want to do as the integral from 0 to 2 pi of cosine theta minus sine theta times the integral from 1 to 2 of r squared times the quantity 4 plus r sine theta dr d theta. So I'm just pulling that cosine theta minus sine theta term out. And let me rewrite that whole integral. So the integral of cosine theta minus sine theta, integral from 1 to 2 of 4r squared plus r cubed sine theta dr d theta. Now again, I need to do the innermost integral first, so don't just try to do this integral and multiply it by the other one. That's not right. This is going to be the integral from 0 to 2 pi of cosine theta minus sine theta. And this integral over here becomes 4/3 r cubed plus 1/4 r to the 4th sine theta evaluated from 1 to 2 d theta. So this integral becomes the integral from 0 to 2 pi of cosine theta minus sine theta times 28 over 3 r cubed plus 15 over 4. Oops, back that up. 20 over 3 period plus 15 over 4 sine theta d theta. And now when we do this last integral, we can FOIL everything out and get integral from 0 to 2 pi of 28 cosine theta over 3 minus 28 over 3 sine theta plus 15 over 4 sine theta cosine theta minus 15 over 4 sine squared theta d theta. And now the only term that's going to survive in this integral is going to be this last term here, the integral of sine squared, which, if I remember my double angle formulas, integrating sine squared is the same thing as integrating 1/2 minus 1/2 of cosine 2 theta. So the only part of the integral that's remaining is negative 15 over 4 times the quantity 1/2 minus 1/2 cosine 2 theta d theta. And again, integrating cosine is going to die on the interval from 0 to 2 pi because of the period. So this integral is just going to be the integral from 0 to 2 pi of 15 over 4 times 1/2. So this is going to be minus 15 pi over 4 is our final answer. Okay, so we've done a couple different examples of integration using our new cylindrical coordinate system. I hope that this made sense, and of course, please reach out if you have any sort of questions at all. Don't forget, as we're going along, to pause your video to let yourself catch up, take notes, and think about what we're talking about. But that's all for now, and I'll see you guys next time.